Every morning, when the rest of the world is slowly waking up, something remarkable happens along the cliffs of the Arabika Massif in the western Caucasus Mountains. For just a brief and quiet interval, the first light of sunrise touches the pale limestone face of the rock. It moves across the stone slowly, almost hesitantly, the way light always seems to behave when it encounters something ancient. The warmth spreads along cracks and ridges that have been forming since long before human memory, and for a few minutes, everything above ground looks perfectly still. Then the light catches a narrow opening in the cliff, not a dramatic archway, not an obvious tunnel, just a modest, unhurried gap in the stone, the kind of opening that a traveler on a mountain path might glance at without stopping. But here the daylight pauses at the threshold. It reaches perhaps a meter or two inside, then simply gives up. Beyond that threshold, the darkness is total, patient, and extraordinarily deep. Somewhere beneath these mountains lies the deepest place humanity has ever reached beneath the Earth's surface. And perhaps many passages still waiting to remain unknown. Welcome to Krubera Cave. Before we begin our descent into this extraordinary place, if you are watching this tonight and you have not yet subscribed to History's Sleepy Time, please do so now. If this kind of storytelling feels right for you, a like on the video helps more people find their way here. And we would genuinely love to know, where in the world are you watching from tonight? Leave your location in the comments. Now, let us go inside. The Arabika Massif sits in the western corner of the Caucasus Range, in the territory of Abkhazia, along the eastern coast of the Black Sea. It is a high limestone plateau, elevated and wind-scoured, the kind of landscape that feels remote even when you are standing directly on it. The rock here is grey-white and dense, built over tens of millions of years from compressed marine sediments. The plateau stretches across roughly 180 square kilometers, and beneath it, hidden within the stone as completely as anything can be hidden, lies one of the most extraordinary cave systems on the planet. From above, the massif looks almost ordinary. There are grasses and low shrubs. There are patches of snow in the higher elevations, even during warmer months. There are the sounds that you might expect from any mountain environment: wind moving across stone, the occasional call of a bird, the distant sound of water somewhere beneath your feet if you listen carefully enough. But that sound of water beneath your feet is important. It tells you something. It tells you that this mountain is not solid. That somewhere beneath the surface, the stone has been hollowed, carved, dissolved, and shaped into a labyrinth that descends so far below the Earth's surface that the very concept of depth begins to feel inadequate. The entrance to Krubera Cave sits at an elevation of approximately 2,256 meters above sea level. This detail matters because the cave itself descends to more than 2,197 meters below that entrance point, reaching down toward and eventually below sea level. The arithmetic alone is staggering, from the narrow opening where sunlight stops to the deepest surveyed chambers. There is a vertical distance of more than 2 kilometers. 2 kilometers of darkness, stone, water, cold air, and silence, existing entirely within the body of a mountain. But in the morning we are imagining tonight, and the many real mornings that expeditions have begun here, none of that depth is visible. You stand at the entrance and you see only darkness. The cave does not reveal itself immediately. It does not open up into a vast chamber just inside the door. Instead, it narrows. It tilts downward. The air immediately changes temperature, and you feel the coolness rising up from below as if the mountain is breathing slowly outward. The smell is of wet limestone and still air, a scent that has no precise equivalent on the surface. It is the smell of a place that has existed without weather, without seasons, without sunlight, for a very long time. Early explorers described that first sensation at the entrance as a strange combination of invitation and warning. The cave was clearly open, it clearly continued, but it also clearly had no interest in making the journey comfortable. The stone was irregular and cold. The passage tilted at angles that required careful footing, and the darkness, once you moved beyond the reach of daylight, was unlike anything most people had experienced before. Not the darkness of a room with the lights off, where your eyes gradually adjust to the ambient glow coming from beneath a door or around a curtain. This was absolute darkness. The kind of darkness that feels physical, that seems to press against your eyes rather than simply fill them. The first question that occurs to anyone standing at that entrance, or even imagining it from the comfort of a warm room tonight, is a simple one. How can a cave continue downward for more than 2 kilometers? What process, operating over what span of time, could possibly carve this much empty space within solid rock? The answer requires us to step back, far back, to a time before these mountains existed at all. Long before the Caucasus Mountains rose from the Earth's surface, long before the first limestone of the Arabika Massif was deposited, this part of the world was covered by a warm, shallow sea. Scientists call it the Tethys Ocean, a vast body of water that no longer exists. That has been slowly consumed by the movement of tectonic plates over hundreds of millions of years, leaving behind only traces of its former presence in the form of fossils, sediments, and chemistry locked within the rock. The Tethys Ocean was not a single stable environment. Over tens of millions of years, it changed depth, temperature, chemistry, and coastline repeatedly. But across many of its shallow zones, something consistent was happening. The shells and skeletons of marine organisms, corals, mollusks, microscopic creatures called foraminifera, were accumulating on the seafloor in vast quantities. These organisms built their structures from calcium carbonate, which is essentially the same mineral we call calcite. When they died, their shells sank. They accumulated in layers. The layers compressed. Over enormous spans of geological time, those compressed layers became limestone, the same pale, dense, slightly porous rock that now forms the Arabika Massif. This process, called carbonate sedimentation, is slow by any human measure. The limestone beneath the Caucasus took tens of millions of years to form. And then, before it could be carved into a cave, something else had to happen first. The limestone had to be lifted. The lifting of rock to form mountain ranges is driven by the collision of tectonic plates, the enormous sections of Earth's outer shell that move slowly but with almost inconceivable force. The Caucasus Mountains began rising roughly 25 to 30 million years ago, when the Arabian tectonic plate began colliding with the Eurasian plate, squeezing and folding the rocks between them. The Tethys seafloor, along with all the limestone it had accumulated, was forced upward, buckled, fractured, and elevated to form some of the highest terrain in Eurasia. This uplift did two things that matter enormously for the story of Krubera Cave. First, it raised the limestone high above sea level, exposing it to rainfall and snowmelt from above. Second, and just as importantly, it fractured the rock. The enormous pressures involved in mountain building cracked the limestone along countless lines and planes, joints, faults, and fissures running in many directions through the rock. These fractures created pathways, and water, given a pathway, will always use it. The process by which water carves caves through limestone is called karstification, and it is one of the more elegant slow processes in all of geology. Rainwater, as it falls through the atmosphere and percolates through soil, picks up carbon dioxide and becomes mildly acidic, a weak solution of carbonic acid. This acidic water enters the fractures in limestone and begins to dissolve the rock very slowly. Calcium carbonate dissolves in acidic water. The fractures widen, the pathways deepen. Over thousands and then millions of years, what began as a hairline crack can become a passage wide enough to walk through, a shaft deep enough to require ropes, a chamber large enough to swallow a building. The Arabika Massif has been undergoing karstification for an extraordinarily long time. Some of the geological processes shaping its current cave network began tens of millions of years ago. Others are still happening today. The water moving through Krubera Cave right now is still slowly dissolving the walls around it, still widening passages by fractions of a millimeter each year, still carving new pathways through the stone in directions that no human has yet followed. This is what makes Krubera Cave so difficult to fully comprehend. It is not a finished thing. It is not an artifact. It is an active geological process that has been running, essentially continuously, since long before the first members of our species walked the earth. The cave we can explore today is simply the current state of a process that began in deep time and continues into the future in ways we cannot fully predict. The depth of Krubera, that extraordinary, almost vertiginous vertical distance from entrance to bottom, is partly a consequence of the massif's elevation above sea level, and partly a consequence of the particular way water has been moving through this specific body of rock. The cave descends because the water descends. It follows gravity, as water always does, seeking the lowest available route through the available fractures. And in the Arabika Massif, the available fractures happen to descend a very long way. Nature spent millions of years preparing this abyss. And it used the simplest possible tools to do it: water, time, and the chemistry of limestone. What has been left behind, after all that patient work, is a wound in the earth that descends so far it almost seems impossible. And yet the cave exists, precisely as the geology predicted it would. To understand Krubera Cave as it exists today, not as a geological curiosity, but as a living, dynamic environment, you have to understand water. Not water as we typically experience it on the surface, flowing in rivers and streams that you can watch and follow and measure in daylight. Underground water is something different. It moves through a hidden architecture of stone, sometimes as a slow seep through porous rock, sometimes as a rushing underground river, sometimes as a still dark lake filling a passage from wall to wall and floor to ceiling. In Krubera Cave, water is present at nearly every level of the descent. Near the entrance, in the upper portions of the cave, you encounter it first as dripping, individual droplets falling from the ceiling, tracing pale mineral trails down the walls, collecting in small basins on the floor. The sound of this dripping is one of the defining sounds of the cave's upper sections. Each drop falls in its own time, at its own rhythm, creating a kind of soft, irregular percussion that echoes slightly in the enclosed space. It is the opposite of silence, and yet somehow it deepens the feeling of quiet rather than disrupting it. As you descend deeper into the cave system, the water becomes more substantial. The dripping gives way to flows, thin streams running along the floor of passages, deepening into proper streams that require careful crossing, and eventually becoming underground waterfalls where passages open into vertical shafts, and the water simply falls freely into the darkness below. These shafts, called pitches in caving terminology, are one of the defining features of Krubera's vertical character. The cave does not descend as a single smooth slope. It descends in stages, through alternating horizontal passages and sudden vertical drops. Some of these drops are modest, a few meters requiring only careful footwork. Others are extraordinary vertical falls of tens of meters, requiring ropes, harnesses, and the kind of focused calm that comes only with experience. The water falling through these shafts has carved them. Over thousands of years, the same water that descends today has been wearing away the stone along those vertical faces, deepening the pitches meter by meter, widening the base of each fall where the impact is greatest. The shaft walls are smooth and pale where the water runs most consistently. They are darker and more textured where the flow is intermittent. Reading the walls of a shaft in Krubera Cave is, in a sense, reading the history of water movement through that particular section of the mountain, a record written in stone over geological time. Deeper in the cave system, the passages begin to encounter what speleologists, the scientists and explorers who study caves, call sumps. A sump is a section of passage that is completely filled with water from floor to ceiling. There is no air space. The passage simply continues, but underwater, for some distance before potentially opening up again into an air-filled space beyond. Sumps are one of the great challenges of deep cave exploration. To pass through them, explorers must dive, bringing scuba equipment or using rebreather systems, in conditions that are extremely confined, extremely cold, and completely dark, except for the light they carry with them. The sumps in Krubera Cave have been among the primary limiting factors in how deep exploration has been able to reach. They are not simply obstacles. They are, in a geological sense, the water table, the level at which all available fractures and passages are completely saturated with water. Moving below the water table in a cave context means moving through the water itself, and the water in these deep sumps is cold, typically around 4 degrees Celsius, and still and dark, and absolutely indifferent to the presence of the humans moving carefully through it. Beyond the sumps, the cave opens again into passages that still hold air, still descend further into the mountain, still offer the possibility of going deeper. It is this alternating rhythm of air passages and flooded sections that gives Krubera its particular character as an exploration target. You never quite know, until you are there, whether the next sump conceals a short flooded section or an impossibly long one. You never know whether the passage beyond the water opens into a new chamber or simply continues downward into another sump. The hydrology of Krubera Cave, the scientific study of how water moves through the system, is itself a subject of active research. Scientists have introduced dye tracers into water entering the cave from the surface and tracked where that dye emerges, trying to map the underground plumbing of the massif. What they have found is that the cave connects to a spring system that emerges near the coast of the Black Sea, several kilometers away and hundreds of meters lower. The water that enters the cave as rain and snowmelt on the high plateau eventually makes its way through the cave's passages, down through the mountain, and out into daylight again, far from where it started. This means that Krubera Cave is not a closed system. It is part of an active, functioning hydrological cycle, a piece of the planet's water system operating underground. Water is continuously moving through it, continuously shaping it, continuously doing the slow geological work that has been happening here since the mountain was first lifted above sea level. The cave is, in this sense, alive. Not alive in the biological sense, though we will come to biological life shortly, but alive in the geological sense. It is actively becoming something. The Krubera Cave of 1,000,000 years from now will be different from the cave of today, shaped by all the water that will have passed through it in the intervening time. Water is the true architect of Krubera. Every passage, every shaft, every chamber, every sump, all of it is the work of water and time, operating on limestone with quiet, patient precision. The explorers who descend into this cave are, in a sense, visitors to the workshop of geology, arriving while the work is still in progress, moving through spaces that are still being shaped. There is a particular kind of courage that belongs specifically to the first explorers of underground places. It is quieter than the courage of a soldier, less visible than the courage of a mountaineer. There are no crowds watching, no summit to photograph against a blue sky, no moment of triumph that can be easily shared or celebrated. The explorer who descends into an unknown cave does so in cold and darkness, moving through passages that have never seen a human face, making decisions based on incomplete information, always aware that the way back out is the same difficult route that brought them in. And in the case of Krubera Cave, that route back out is measured in kilometers of vertical ascent through cold stone and rushing water. The recorded history of exploration in the Arabika Massif begins in the mid-20th century, though local people had certainly known of various cave openings in the plateau for far longer. Soviet speleologists, caving scientists and explorers working within the scientific institutions of the Soviet Union began systematic exploration of the Massif's cave systems in the 1960s. This was a period of significant scientific ambition in the Soviet Union, and the exploration of cave systems was considered a legitimate and valuable field of scientific inquiry. Teams of trained cavers, equipped with the rope systems, carbide lamps, and physical conditioning of the era, began methodically exploring the openings they found across the Arabika Plateau. The cave that would eventually become known as Krubera was first entered by a Soviet expedition in 1960. The team, led by a Georgian speleologist named Alexander Krubera, after whom the cave would later be named, found an entrance and descended into the opening passages. But the technology and techniques available at the time limited how far they could go. The pitches were deep, the cold was significant, and the rope systems of the 1960s were not designed for the sustained vertical work that Krubera would eventually demand. The team documented what they found, mapped what they could reach, and returned to the surface with a partial picture of a cave system that clearly continued far beyond what they had been able to explore. Over the following decades, the cave attracted periodic attention from Soviet caving expeditions, each one pushing slightly further than the last. But progress was slow, measured in tens of meters rather than hundreds, and the cave's true depth was not yet apparent. The geology was complex. The passages twisted and branched. Some directions led to dead ends, chambers that simply stopped, walls with no onward passage. Others led to pitches that went deeper, but reaching the bottom of those pitches required equipment and planning that took years to assemble. It is worth pausing here to appreciate what those early expeditions were doing in a practical sense. Cave exploration at depth is logistically extraordinary. Every meter of rope must be carried in. Every piece of equipment, food, sleeping gear, lights, cameras, survey instruments, must be physically transporting through the cave's passages, lowered down its pitches, hauled across its sumps. The explorers themselves must climb down on the way in and climb back up on the way out, using rope ascenders, mechanical devices that grip the rope and allow a climber to move upward on a fixed line to make the vertical sections manageable. A descent that takes several hours going in might take twice as long coming out, with tired muscles and diminishing food supplies. The collapse of the Soviet Union in 1991 disrupted many scientific programs, and cave exploration in the Caucasus was no exception. But international interest in the Arabika Massif had been growing, and the 1990s saw a new phase of exploration begin, one involving teams from Ukraine, Russia, Georgia, and eventually other countries working sometimes collaboratively and sometimes independently, each contributing to the growing understanding of how deep the cave might actually go. The Ukrainian Speleological Association became particularly significant in this period. Under the leadership of Yuri Kazyan, Ukrainian cavers began mounting systematic expeditions to Krubera in the late 1990s and into the 2000s. These expeditions were characterized by extraordinary preparation and a methodical approach to the problem of depth, not rushing for a single dramatic breakthrough, but carefully establishing camps at successively deeper levels, allowing longer and more thorough exploration of each section before pushing further. The establishment of underground camps was a critical development. Rather than descending from the surface each day and returning each evening, which would have been physically impossible at the depths being reached, teams began setting up sleeping camps at various points within the cave. These were not comfortable accommodations. An underground camp in Krubera Cave typically consisted of lightweight tents erected on whatever flat surface was available, sometimes a narrow ledge beside a stream, sometimes a flat section of passage floor, with sleeping bags designed for extreme cold. Food that could be prepared with minimal equipment and the constant sound of dripping water and distant waterfalls as a backdrop to sleep. Imagine, for a moment, what it would mean to sleep in such a place. You are hundreds of meters below the surface. The temperature around you is perhaps 4 or 5 degrees Celsius. The air is completely still and saturated with moisture. There is no natural light of any kind, not even the faint glow that you might perceive through closed eyelids in a dark room above ground. The darkness is total. The sounds are entirely geological, water moving through stone, the occasional settling of rock, the dripping and flowing that never stops. And somewhere above you, through kilometers of cold stone and vertical shafts, is the surface of the earth, with its weather and its daylight and its human activity. That surface feels, in such a camp, not just distant, but almost abstract, like something remembered rather than something real. In 2001, a Ukrainian expedition achieved a milestone that drew international attention. The team pushed Krubera's known depth past 1,000 meters, making it the first cave confirmed at that time to exceed 1 kilometer in depth, and placing it among the deepest known caves in the world. The achievement was documented, verified by survey measurements, and published in the speleological community. But even as the announcement was being made, the teams on the ground knew that the cave continued. The passages did not stop at 1,000 meters. They kept going. Each subsequent expedition revealed only another layer of the cave, another pitch descending beyond the previous limit, another sump that concealed an air-filled passage beyond, another chamber that opened onto yet more dark and unmapped stone. The pattern was consistent and, in its own geological way, almost poetic. The cave seemed to respond to each breakthrough with another question. You have reached this far, it seemed to say, but here is another passage. Here is another shaft. Here is more darkness beyond the darkness you have already crossed. By 2004, Ukrainian expeditions had pushed the known depth of Krubera past 1,800 meters. By 2007, past 2,000 meters. These were extraordinary achievements, depths that had never been reached in any cave on Earth. And they were achieved not through a single dramatic push, but through years of methodical, patient, exhausting work by teams of explorers who spent weeks at a time underground, living in conditions that most people would find difficult to imagine. The question that was forming in the caving community during this period was not simply how deep Krubera might ultimately prove to be. It was something more subtle. The cave was descending in a way that suggested there might be no natural stopping point, or at least no stopping point determined by the cave's structure rather than by the limitations of exploration technology. Each time a sump was passed or a new pitch explored, the cave continued. The question of where it ended, if it ended at all within reach of human exploration, remained genuinely open. Each expedition had revealed only another layer, and beneath each layer, another. There is a question that any thoughtful person might ask when considering a place like Krubera Cave. And it is a question that occurs naturally somewhere in the descent, past the point where daylight fades past the first pitches and the first underground streams, somewhere in the middle depth of the cave, where the surface world feels truly and completely left behind. The question is this: in a place where sunlight never arrives, where there is no photosynthesis, no plants, no seasonal cycle, no warmth from the sun, can anything live? The answer, as biology has repeatedly demonstrated in the most extreme environments on Earth, is yes. Life is extraordinarily persistent. It finds ways to exist in conditions that seem, from a human perspective, completely hostile. And in Krubera Cave, life exists, quietly, slowly, invisibly to casual observation, but genuinely and continuously. The biological community of Krubera Cave was not well studied until relatively recently. The cave's extreme depth made biological sampling difficult. Reaching the lower sections required the same logistical effort as the caving expeditions themselves, and biologists are not always trained cavers. But as exploration deepened and expeditions became more systematic, biological sampling became part of the scientific work. And what emerged was a picture of life adapted to permanent darkness in ways that are both elegant and scientifically significant. In the upper sections of the cave, closest to the entrance, the biological community is relatively diverse and connected to the surface ecosystem. Insects and other invertebrates that inhabit the entrance zone use the cave as shelter without being fully dependent on it. Cave crickets, for example, long-legged, delicate creatures with extraordinary antennae, move between the cave and the outside world, feeding on organic matter near the entrance and retreating into the cave's protected environment when conditions on the surface are harsh. They are not true cave dwellers in the biological sense. They are opportunists, using the cave as a resource without committing to it completely. Deeper in the cave, however, the biological community becomes genuinely cave-adapted, and this is where the science becomes particularly interesting. Among the species discovered in Krubera Cave are crustaceans belonging to groups that, in their surface relatives, would live in streams and small bodies of water. In the cave environment, these crustaceans have undergone the adaptations typical of deep cave fauna: reduced or absent eyes, often pale or translucent bodies with reduced pigmentation, extended appendages that serve as sensory organs compensating for the absence of vision. These are not recent adaptations. The process of cave adaptation takes thousands of generations, which, for small invertebrates, might mean tens of thousands of years. The crustaceans living in the deep passages of Krubera Cave have been adapting to this environment since long before any human explorer arrived. Among the most scientifically significant biological discoveries in Krubera Cave was a tiny, wingless insect called Plutomurus ortobalaganensis, a species of springtail found at depths exceeding 1,900 meters below the surface. At the time of its discovery and description, this represented the deepest known terrestrial animal ever recorded. The finding generated genuine excitement in the scientific community, not simply because of the depth record, but because of what it implied about the distribution of life in extreme subsurface environments. If a complex, multicellular animal could sustain itself at nearly 2 kilometers below the Earth's surface, what did that suggest about the potential distribution of life in other subsurface environments, on Earth and perhaps elsewhere? The question of how these deep cave animals sustain themselves is inseparable from the question of energy. At the surface, almost all ecosystems are ultimately powered by sunlight through photosynthesis. But in a cave where sunlight never arrives, photosynthesis is impossible. The energy that sustains life in Krubera's deep zones comes from two primary sources: organic material carried in by water from the surface, and microbial communities that can extract energy from chemical reactions rather than from light. The water flowing through Krubera Cave carries dissolved organic matter, the remnants of plant material, soil bacteria, and other biological material from the surface above. This dissolved organic matter is the food source for microbial communities in the cave's water and sediments, and those microbial communities are in turn the food source for small invertebrates, which are in turn available as prey for slightly larger organisms. It is a food web built not on sunlight, but on chemistry and water transport, thin, fragile, and slow, but genuinely functional. Cave spiders have been documented in Krubera, hunting in the darkness for smaller invertebrates. Their webs are not built to catch flying insects, as surface spiders might construct them. They are built across water surfaces or along passage walls, designed to intercept the small crawling and swimming creatures that represent the available prey in this lightless world. These spiders navigate entirely by touch and chemical sensing. In a world without light, vision would be wasted biological investment, and natural selection over thousands of generations has gradually reduced or eliminated the eyes of many cave-dwelling species. Microbial life in Krubera deserves particular attention because it operates at a scale and in ways that are largely invisible to casual observation, but scientifically profound. Microbial communities in deep cave environments can subsist on chemical energy sources, iron compounds, sulfur compounds, dissolved minerals in water, through processes collectively called chemolithotrophy. These microbes form thin films on rock surfaces and in water, processing the chemical environment around them, and in doing so, creating conditions that other organisms can exploit. They are the base of the food web in sections of the cave where even dissolved organic matter from the surface is too dilute to support more complex life directly. Life continues even where sunlight never arrives. It continues in reduced form, in slowed form, in forms adapted beyond easy recognition to the particular conditions of permanent cold and darkness. But it continues. And that continuity, that stubborn biological persistence in one of Earth's most extreme environments, is one of the quieter scientific wonders of Krubera Cave. Let us descend now into what it actually means, physically and psychologically, to be deep inside Krubera Cave on a serious scientific expedition. Let us move away from the geology and the biology for a moment and consider the human experience of this place, because the explorers who have pushed Krubera's known depth to its current limits were not simply operating scientific instruments. They were living, breathing, feeling human beings in an environment that challenged them at every level. The cold is perhaps the first thing to understand. At depths below a few hundred meters in Krubera Cave, the temperature stabilizes at around 4 to 5 degrees Celsius throughout the year. This is cold, cold enough to cause genuine hypothermia if a climber's equipment becomes wet and they remain inactive for an extended period. And in a cave where water is constantly present, where every passage has some degree of moisture, where waterfalls must sometimes be climbed through directly, where sumps must be dived, the management of body temperature becomes a constant practical concern. Expedition members in Krubera wear layers of insulating material beneath their caving suits, but there is a limit to how warm you can dress when you also need to move freely through tight passages and climb vertical ropes. The cold is simply part of the environment. It must be accepted and managed rather than eliminated. The physical demands of vertical work are extraordinary. A single pitch of 50 meters, a vertical drop of half the height of a typical office building, requires careful rigging of the rope at the top. A controlled descent on a mechanical descender device, and then critically the ability to ascend the same rope on the way back out. Rope ascent is significantly more demanding than descent. Using mechanical ascenders, devices that grip the rope and allow upward movement, a climber essentially performs a vertical movement equivalent to climbing a ladder of that height, one step at a time, with the full weight of their pack pulling them down. At depth in Krubera, after days or weeks of physical work in cold and wet conditions, this ascent becomes a test of a very specific kind of endurance. The logistics of an expedition to the deep sections of Krubera Cave are breathtaking in their complexity. Expeditions typically involve large teams, sometimes 30 to 50 people, divided into different roles. Surface teams manage the entrance and coordinate with the outside world. Intermediate teams ferry supplies down through the upper sections of the cave. Lead teams push to the deepest points, supported by the layers of logistical work happening above them. Everything, every meal, every piece of rope, every tank of air for diving, every item of camping equipment must travel the same route as the explorers themselves, carried by hand through the cave's passages and lowered down its pitches. At the deepest underground camps, the isolation becomes something almost tangible. Explorers have described the experience of being at a camp 1,500 or 1,800 meters below the surface as a kind of profound quietness of context, a sensation not of being trapped, but of being genuinely and completely separate from the surface world. There is no communication with the outside except through a relay of messages passed up through the cave by other team members. There is no natural light, no weather, no sense of day or night. The rhythms of eating and sleeping must be managed by watch and by discipline rather than by any external cue from the environment. Sleep in such a camp is its own experience. The tent provides some insulation from the cold ground and the moist air, but it does not eliminate the sound of the cave. Dripping water continues through any sleeping period. Underground streams audible nearby continue their flow. Occasionally, the sound of a rock dislodged somewhere above or below will echo through the passage. And the darkness is absolute, the same darkness that surrounded you when you were moving through the cave is the same darkness that surrounds you when you close your eyes to sleep. There is no distinction, in darkness this complete, between eyes open and eyes closed. What is remarkable about the accounts of experienced cavers who have spent extended periods underground in conditions like these is not how alien they found the experience. It is how, after a few days, the cave began to feel normal, not comfortable, never entirely comfortable, but normal. The rhythms of the underground day settled into a pattern. The sounds became familiar. The cold became expected. The darkness ceased to be frightening and became simply a feature of the environment, managed with lights that were never switched off except during sleep. This normalization speaks to something important about human adaptability. We are surface animals, built for daylight and weather and the social context of other people. But we carry within us a capacity to adjust to almost any stable environment, given sufficient time and sufficient competence. The explorers who spent weeks in Krubera's deep sections were not superhuman. They were trained, experienced, and carefully selected, but they were human beings, and their bodies and minds adjusted to the cave environment in the same fundamental ways that human bodies and minds have always adjusted to difficult environments throughout history. The deeper explorers traveled, the more the surface felt distant, not as a frightening thought, but as a simple geographical fact. The surface was there. It would still be there when they returned, but for now, it was irrelevant. What mattered was the passage ahead, the rope that needed to be rigged, the sump that needed to be assessed, the survey data that needed to be recorded. The work of exploration at depth is intensely present-focused. The cave demands your full attention at every moment, and that demand is, in its own strange way, one of the things that experienced explorers have described as deeply satisfying about the work. There is a particular kind of problem that faces anyone who tries to describe a cave to someone who has never been inside one. The problem is not vocabulary, and it is not imagination. The problem is that caves do not conform to the shapes and geometries that human minds are accustomed to working with. We are surface creatures. We think in terms of horizontal distances, the length of a road, the width of a field, the span of a bridge. We are comfortable with height as a concept because we can look up at a building or a cliff and perceive its scale directly. But depth, true depth, measured downward into stone, is something that our spatial intuition handles poorly. We cannot look down into Krubera Cave and perceive its scale. We can only measure it. The science of measuring and mapping caves is called cave surveying, and it is one of the more technically demanding disciplines within speleology. In principle, the process is straightforward. You move through a cave passage from point to point, measuring the distance between each pair of points, the compass bearing of the line between them, and the angle of inclination, whether the passage is horizontal, sloping upward, or sloping downward. You also record the dimensions of the passage at each measurement point, how wide, how high, how far the walls are from the centerline of your survey. From these measurements, processed through appropriate mathematics, you can construct a three-dimensional model of the cave's geometry. In practice, the process in a cave like Krubera is enormously complicated. Passages are not straight. They twist and branch and occasionally reverse direction. Pitches descend at angles that make precise measurement difficult. Sumps break the continuity of the survey, requiring separate measurement of underwater sections using specialized techniques. And all of this work is being done in cold, wet, dark conditions by people who are also managing the physical demands of moving through the cave, climbing ropes, crossing streams, navigating tight sections that require removing packs and pushing them through separately before following. Survey work in Krubera has been accumulated over decades of expeditions, each one adding new data to the growing picture of the cave's geometry. The survey data is recorded in field notes and transferred to computer models that allow the three-dimensional structure of the cave to be visualized and analyzed. These computer models are extraordinary objects, intricate, branching, three-dimensional structures that look, from certain angles, like the root system of an enormous tree or the vascular network of some vast organism. They show the cave's passages winding through the limestone, branching and rejoining, descending in steps through the pitch sequences, spreading laterally through the horizontal sections. The depth figure that appears in scientific publications and reference sources, the figure that makes Krubera the deepest known cave on Earth, is not a single measurement made with a tape measure from top to bottom. It is the result of a continuous survey carried out over many expeditions, connecting thousands of individual measurement points into a coherent three-dimensional model, from which the vertical distance between the highest and lowest surveyed points can be calculated. This calculation must account for the cave's complex three-dimensional geometry, the way passages sometimes ascend slightly before descending again, the way the cave's overall direction of descent is not a straight vertical line, but a complex three-dimensional path through the rock. The precision of this survey work matters because cave depth records are genuinely contested and scientifically significant. The difference between the deepest cave and the second deepest cave might be measured in tens of meters. A surveying error of that magnitude, propagated through thousands of measurement points, is entirely possible. This is why expeditions to record-setting caves invest significant effort in verification, returning to previously surveyed sections and resurveying them with improved instruments to confirm or refine previous measurements. Modern cave surveying has been transformed by technology. Laser distance meters, devices that measure distance by timing the reflection of a laser pulse, have replaced tape measures in many applications, allowing faster and more precise measurement of passage dimensions. Digital data loggers record survey measurements directly in electronic form, eliminating transcription errors. Three-dimensional laser scanners, developed for applications in architecture and engineering, have been adapted for cave surveying and can produce extraordinarily detailed point cloud models of cave passage geometry. These tools have not eliminated the physical challenge of getting survey equipment into a deep cave. Every instrument still has to be carried down through the same pitches and sumps as the explorers themselves, but they have dramatically improved both the speed and the accuracy of the survey work once it begins. The question that arises from all this careful measurement is a deceptively simple one. How do you measure a place that still refuses to end? The survey of Krubera Cave extends to the deepest point that exploration has physically reached, the point where a sump or a physical limitation of the passages has prevented further progress. But beyond that point, the cave almost certainly continues. The water flowing through those passages has to come from somewhere and has to go somewhere. The geological structure of the Arabika Massif does not simply terminate at the deepest surveyed point. The rock continues, and the fractures within it continue, and the water moving through those fractures continues its patient journey toward the coast. This is the quietly unsettling truth at the heart of any map of Krubera Cave. The map ends where human exploration ends. But the cave does not end where the map ends. Beyond the last surveyed passage, beyond the deepest measured chamber, there is more. How much more is unknown? Whether that additional cave is accessible to human exploration with current or foreseeable technology is also unknown. The map of Krubera Cave is, in the most precise scientific sense, incomplete, and may remain incomplete for a very long time. Scientific collaboration has been essential to the mapping effort. Ukrainian, Russian, Georgian, and international teams have all contributed survey data, and the integration of that data across different expeditions conducted in different years, using different instruments and different survey conventions, has been a significant scientific undertaking in itself. The cave surveying community has developed international standards for data recording and processing precisely to make this kind of integration possible, so that the work of one expedition can be meaningfully combined with the work of another, building a cumulative picture that no single expedition could produce alone. There is something quietly moving about this collaborative dimension of cave mapping. The map of Krubera Cave is not the work of any single person or any single team. It is the accumulated result of decades of work by hundreds of people, scientists and explorers from many countries, operating in difficult conditions, motivated by a shared desire to understand what lies beneath the Arabika Massif. Each survey point in the dataset represents a moment when a cold, wet, tired explorer in the darkness of the cave paused to take a measurement, to add one small, precise piece of data to the collective understanding of this place. That collective understanding, rendered as a three-dimensional map, is one of the genuine scientific achievements of deep cave exploration. It is a portrait of a hidden world, drawn with instruments and mathematics, representing the shape of something that no human eye can perceive in its entirety. And it is still being drawn. The mountains of the Western Caucasus have been inhabited by human communities for thousands of years. The peoples of this region, the Abkhazians, the Georgians, the various groups of the North Caucasus highlands, have lived alongside these limestone massifs, herded animals across their high plateaus, and found shelter in their lower valleys through all the seasons of many centuries. And in all that time, the caves and openings in the rock have not been invisible to them. They have been noticed, wondered at, and in the way of all human cultures confronting mysterious natural phenomena, incorporated into story. It is important to say clearly, as we move into this part of our story, that what follows is folklore, oral tradition, cultural memory, and the kinds of stories that communities have always built around the features of their landscape. These stories are not geological evidence. They are not scientific accounts. They are something different, and in their own way equally valuable. They are the record of how human imagination has responded to the presence of a deep, dark, mysterious opening in the earth, across generations of people who had no way of knowing how deep that opening actually went. In Abkhazian oral tradition, caves and underground spaces occupy a complex and sometimes ambiguous place. The earth itself is understood in some traditional accounts as a layered place, a world above, the world of ordinary human life, and worlds below that are inhabited by spirits, ancestors, or forces that are neither entirely benevolent nor entirely threatening. Caves are understood, in some of these traditions, as thresholds, places where the boundary between the ordinary world and these deeper realms is thin or permeable. Entering a cave in such a cultural framework is not simply a physical act. It carries a kind of existential weight. Shepherds who have grazed animals on the Arabika plateau across many generations have their own relationship with the openings in the limestone. The high plateau is honeycombed with cave entrances, some small and easily overlooked, others more prominent. Livestock occasionally fall into these openings, and the recovery or loss of animals through cave entrances has been a practical concern of plateau herders across many centuries. In the oral accounts collected from communities near the Massif, stories circulate about animals and occasionally people who fell into cave openings and were never recovered, or who emerged far from where they entered, disoriented, and unable to explain their journey. These stories almost certainly reflect genuine encounters with the cave system. An animal that falls into a cave entrance follows a water course through passages and emerges at a spring outlet kilometers away is doing something that hydrologists now understand perfectly. It is following the underground drainage of the karst system. But to a shepherd without knowledge of speleology, such an event would be extraordinary and inexplicable. The animal went into the mountain and came out somewhere else entirely. It is easy to understand why such events would accumulate into stories about the mysterious underground world and its hidden connections. The echoes within caves have also contributed to cultural imagination. Sound behaves strangely in cave environments. A voice spoken in a certain chamber will return as multiple echoes from different directions, in different timings, as the sound bounces from walls and ceilings of irregular geometry. Dripping water in a large chamber creates sound that seems to come from everywhere and nowhere. The sound of an underground river, heard through a wall of rock, can emerge as a muffled, rhythmic sound that is difficult to identify or locate. For people who understood these sounds without the framework of geology and acoustics, Such phenomena could easily become evidence of presences, underground voices, hidden communities, the speech of entities that lived within the mountain. There are also traditions in some Caucasus communities of specific caves being considered sacred or forbidden, places where ordinary people were advised not to go, where the permission or guidance of particular individuals was required for safe passage. These traditions likely reflect a practical wisdom about the dangers of cave exploration, the risk of falls, of getting lost, of hypothermia in cold underground water, encoded in cultural prohibitions rather than explicit safety warnings. The language of the sacred and the forbidden is, in many traditional cultures, the language in which practical danger is communicated. None of these traditions tell us anything specific about Krubera Cave's geology or hydrology or the biology of its deep passages. But they tell us something that is perhaps equally interesting, that the people who lived alongside this mountain for centuries were not indifferent to it. They noticed its openings. They wondered about its depths. They built stories around its mysteries. The impulse to probe the unknown, to reach into the darkness and try to understand what lies within it, is not uniquely modern or uniquely scientific. It is a deeply human impulse, and it has been operating in relationship to the Arabika Massif for far longer than the history of scientific speleology. The whispers in the chambers of Krubera Cave, the echoes of dripping water, the resonance of underground rivers heard through the stone, predate any human presence in those chambers by an enormous span of time. They have been occurring in absolute darkness throughout the entire period of human occupation of the Caucasus region. The communities living above the cave were separated from those sounds by hundreds of meters of solid rock. They could not hear them. But they sensed, in the way that people always sense the presence of something large and hidden nearby, that the mountain contained something, and they were right. Beyond its significance as a record of human endurance and exploration, beyond its cultural resonance and its extraordinary geology, Krubera Cave is something that scientists across several disciplines have come to value deeply, a natural laboratory of remarkable quality and extraordinary rarity. The properties that make the cave difficult to explore are, from a scientific perspective, precisely the properties that make it so scientifically valuable. Its depth, its isolation from the surface, its stable physical environment, and its active hydrology combine to create conditions in which certain kinds of scientific questions can be addressed with a clarity that is simply not available anywhere else. Consider the cave's climate. At depth, Krubera's temperature is stable, consistently around 4 to 5 degrees Celsius throughout the year, unaffected by surface temperature fluctuations, by seasons, by daily warming and cooling cycles. This thermal stability is the result of the cave's depth and the insulating properties of the surrounding rock. The enormous mass of limestone above acts as a thermal buffer, preventing surface temperature changes from penetrating to the cave's lower sections. This stable thermal environment means that experiments conducted in the deep cave are not confounded by temperature variation, a significant advantage in many areas of scientific research. The cave's atmosphere is also of scientific interest. Deep cave air is isolated from the surface atmosphere except through the very slow mixing that occurs through cave passages and fractures. This means that the cave's atmosphere can develop distinctive chemical characteristics, elevated carbon dioxide concentrations, for example, derived from the respiration of organisms in the cave and from the chemistry of water dissolving limestone. Measuring and understanding these atmospheric characteristics contributes to the broader scientific understanding of subsurface carbon cycling, one of the important components of Earth's global carbon budget. Speleothems, the mineral formations that grow in caves, including stalactites and stalagmites, are among the most scientifically valuable features of any cave environment, and Krubera contains them in various sections of its upper and middle levels. Speleothems grow by the slow deposition of calcite from water dripping through the cave. Each year's growth adds a thin layer to the formation, and the chemistry of that layer reflects the environmental conditions at the time of its deposition. The temperature, the amount of rainfall, the carbon isotope ratios in the atmosphere and soil above. Over thousands of years, these layers accumulate to form a continuous record of past environmental conditions, a climate archive encoded in stone. Reading this archive requires extracting tiny samples from speleothems and analyzing their chemistry with high-precision instruments. The ratios of different oxygen isotopes in the calcite layers reflect past rainfall patterns. The ratios of carbon isotopes reflect past vegetation cover and soil conditions. The presence or absence of certain trace elements reflects past soil chemistry and temperature. By analyzing these proxies, indirect chemical records of past conditions, scientists can reconstruct the environmental history of the region above the cave across timescales of thousands to hundreds of thousands of years. This kind of paleoclimate record from caves in the Caucasus region is scientifically significant because the Caucasus sits at the boundary of several important atmospheric circulation systems. Moisture from the Black Sea, air masses from the Mediterranean, continental air from Central Asia, and Arctic air from the north all interact in this region, making it sensitive to changes in large-scale atmospheric circulation patterns. A high-resolution climate record from the Arabika Massif can therefore contribute to understanding how these circulation patterns have changed over time. Information that is relevant to understanding past climate variability, and by extension, to understanding the range of natural climate variation within which human civilization has developed. The microbiology of Krubera Cave is an area of active and genuinely exciting research. The microbial communities in the cave's water and on its rock surfaces represent a largely unstudied ecosystem, one that has been evolving in isolation from the surface biosphere for an extraordinarily long time. These communities may contain microbial species that have never been described by science, along with novel metabolic processes, novel biochemical compounds, and novel ecological relationships that could be significant for both basic science and practical applications. The study of cave microbiology has, in recent years, generated significant scientific interest beyond the caving community. Some cave microbes produce antibiotic compounds that are effective against bacterial strains resistant to conventional antibiotics. The metabolic processes used by chemolithotrophic cave microbes, those that extract energy from chemical reactions rather than from light, have relevance to the search for life in extreme environments elsewhere in the solar system. The subsurface of Mars, for example, where liquid water may exist in protected niches below the frozen surface, could potentially host microbial communities operating on principles similar to those found in deep earth caves. Krubera, as one of the deepest and most thoroughly studied deep cave environments on Earth, provides a useful reference point for thinking about what life in such environments might look like. The groundwater chemistry of the cave system is another active research area. Water moving through the cave dissolves minerals from the surrounding rock, accumulates organic compounds from biological activity, and mixes with water from different source areas on the surface above. Analyzing the chemistry of cave water at different depths and locations within the system allows scientists to trace the movement of water through the karst aquifer, understanding which surface areas contribute water to which sections of the cave. How long water spends underground before emerging at the spring system on the Black Sea coast, and how the aquifer responds to changes in surface conditions such as rainfall patterns or land use changes. Krubera is one of Earth's greatest underground laboratories, not because it was designed or built for scientific purposes, but because the geological processes that created it happened to produce an environment of exceptional scientific value. The cave asks questions of its scientific visitors just as surely as it asks questions of its explorers, and the answers to those questions are still, in large part, being assembled. There is a version of this story that ends cleanly. Explorers found a cave, they measured its depth, they established a record, they published their findings and moved on to other questions. That version of the story is tidy and satisfying and almost entirely misleading. Because the truth of Krubera Cave, the truth that any honest scientist or experienced caver will tell you quietly, without drama or exaggeration, is that the exploration of this place is not finished. It may not be finished for a very long time. And the reasons why it is not finished tell us something important about the relationship between human curiosity and the natural world's capacity to exceed it. The deepest point that human explorers have physically reached within Krubera Cave stands at a depth of approximately 2,197 meters below the entrance. This figure has been refined across multiple expeditions and represents the current surveyed depth of the cave system. It is a genuinely extraordinary number, deeper than any other known cave on Earth, deeper than the height of many significant mountain peaks measured from their bases. Deep enough that the weight of rock above your head, if you pause to think about it at that depth, becomes a concept that is easier to feel than to calculate. But that number, 2,197 meters, does not represent the bottom of the cave. It represents the bottom of the explored cave. These are not the same thing, and the distinction matters enormously. The passages of Krubera Cave do not terminate at 2,197 meters with a solid wall of rock. They terminate at their deepest accessible point in a sump, a flooded passage where the water fills the space completely and human progress requires diving. This particular sump, in the deepest section of the cave, has been entered and partially explored by cave divers, specialists who combine the technical skills of deep cave exploration with the equipment and training of scuba diving. What they have found is that the sump continues. It does not end quickly. It extends into the darkness in a direction that the geometry of the cave system and the logic of the underlying hydrology suggest leads to additional air-filled cave passages beyond. Cave diving in a sump at 2,197 meters depth is among the most technically demanding activities that human beings currently undertake. The diver must carry all their breathing gas, all their lighting, and all their equipment through the same route that brought the surface expedition to this point, down through all the pitches, through all the upper sumps, along all the passages. By the time a diver reaches the deepest sump in Krubera, they have already completed an exhausting multi-day journey underground. The dive itself is then conducted in absolute darkness, in near-freezing water, in a passage whose geometry may be complex and whose extent is unknown, with no possibility of external assistance if something goes wrong. The limitations are not primarily about courage or skill. The explorers and divers who have worked in Krubera Cave possess both in extraordinary measure. The limitations are technical and physical. Diving equipment has finite capacity. There is a limit to how much breathing gas a diver can carry while still being able to move through a confined underwater passage. There is a limit to how far from the air-filled passage a diver can safely travel given the gas supply available. And there is a limit, ultimately, to how long a human body can sustain the physiological stress of deep cave diving in cold water before the risk of error or accident becomes unacceptably high. New expeditions continue to approach these limitations with improved technology. Rebreather systems, devices that recycle exhaled gas rather than venting it, dramatically extending the duration a diver can remain underwater on a given gas supply, have opened new possibilities in cave diving generally and have been applied in the deeper sections of Krubera. Side-mount diving configurations, in which tanks are carried alongside the body rather than on the back, allow divers to pass through narrower passages than traditional equipment permits. These technological improvements have been genuinely significant, and they have allowed divers to push further into the summits of Krubera than would have been possible even a decade ago. But the cave has responded to each technological advance by revealing more of its extent. The sump continues beyond the furthest point any diver has reached. The passage continues beyond the furthest point any diver has measured. The water flowing through that passage is going somewhere that the hydrological evidence suggests is a further section of air-filled cave that might, in turn, descend still deeper into the Arabika Massif before eventually connecting to the spring system at the coast. How much deeper could Krubera ultimately prove to be? This is a question that scientists approach with appropriate caution. The geological structure of the Arabika Massif does not, in principle, prevent the cave from extending significantly deeper than its current known depths. The massif's limestone extends well below sea level, and karst cave systems in other parts of the world have been found to extend below sea level in their lower sections. The spring outlet of Krubera's water system is near sea level, which suggests that the cave's drainage ultimately reaches approximately sea level before emerging. If additional cave passages exist below the current explored depth, as the evidence strongly suggests, they could potentially extend for hundreds of additional meters before reaching the level of the coastal spring system. Beyond the flooded passages, there is also the question of unmapped side passages in the sections of the cave that have already been visited. Krubera is not a single corridor descending neatly from entrance to bottom. It is a complex branching system, and the mapping of its lateral extent is significantly less complete than the mapping of its main descending route. Side passages branch off from the main system at many levels, some explored, many not. Some of these side passages may terminate quickly in impenetrable rock or sediment. Others may connect to additional sections of cave that have never been visited, never been measured, never been recorded in any scientific document. The exploration of these lateral sections of the cave requires a different approach from the linear push for depth that characterizes record-setting expeditions. It requires the patience to explore carefully at a given level rather than always pushing downward, to follow side passages to their conclusions, to map what is there rather than simply noting that something is there and moving on. This kind of systematic lateral exploration is scientifically valuable even when it does not produce dramatic depth records, because it contributes to a complete understanding of the cave system's three-dimensional structure and hydrology. There are also sections of the cave where the passages narrow to dimensions that current exploration technology cannot pass through. A crack in the rock that is wide enough for water to flow through but too narrow for a human body to enter might connect to a substantial cave passage just a meter or two beyond the point of constriction. Enlarging such a constriction through careful mechanical work, a practice called digging or pushing that has a long history in cave exploration, is sometimes possible and sometimes not, depending on the nature of the rock and the geometry of the constriction. In Krubera, there are documented locations where such constrictions have frustrated explorers who could feel the air movement from beyond, could sense, through that cold breath of air from the darkness, that more cave existed just out of reach. The technology that may ultimately advance exploration in Krubera's inaccessible sections is still being developed. Miniaturized robotic systems, small enough to pass through constrictions that human explorers cannot, have been proposed and are being developed for cave exploration applications. Autonomous underwater vehicles small enough to operate in cave diving conditions could potentially survey flooded passages well beyond the range of human divers. These technologies are not yet mature enough for deployment in an environment as demanding as Krubera's deep sections, but the trajectory of their development suggests that within the coming decades, some of the cave's currently inaccessible sections may become reachable through means other than direct human physical presence. What those sections might contain, whether they lead to additional depth, to significant biological communities, to scientific records of geological or climatic value, is genuinely unknown. Not theoretically unknown, in the way that many scientific questions are technically open while their answers are effectively predictable. Genuinely unknown, in the sense that no human being has any direct evidence about what lies in those passages, and the indirect evidence from hydrology and geology is consistent with a wide range of possibilities. This genuine unknowing is, in a scientific culture that prizes the accumulation of knowledge, a somewhat unusual condition. We are accustomed to the idea that the frontiers of knowledge are at the edges of what we can perceive, at cosmological scales, at quantum scales, in the complexity of biological systems. The idea that a place on Earth's surface, accessible by a walk across a limestone plateau, conceals within it a physical space that no human being has ever visited is remarkable. And yet, that is precisely the situation at Krubera Cave. A few hundred meters beyond the current limit of exploration, in directions that can be approximately inferred from the available evidence, there are passages and chambers that exist in the same complete ignorance that every cave on Earth existed in before the first human ever entered a cave. The stone is there, the darkness is there, the water is there, and no human knowledge touches any of it. It would be tempting, having established all that Krubera Cave is and all that it represents, to ask a straightforward question: why does it matter? Why should any of us, living our ordinary surface lives in ordinary surface daylight, care about the passages of a cave in the Western Caucasus that most of us will never visit, and that has no practical effect on our daily existence? The answer to that question is not a simple one, and it operates at several different levels simultaneously. Some of those levels are immediately practical, others are more abstract, but in certain ways equally important. At the most practical level, Krubera Cave matters because of what it contains and what it records. The speleothems of its upper sections hold climate records that extend back through multiple glacial and interglacial cycles, records of how the regional climate has changed in response to large-scale shifts in the Earth's orbital parameters, ocean circulation patterns, and atmospheric composition. Understanding these past climate changes is directly relevant to understanding the range of natural climate variability that the Earth's systems are capable of producing. It provides context for interpreting the climate changes that are currently occurring due to human activity, not to diminish the significance of those changes, but to understand them with appropriate scientific depth. The microbiology of the cave's deep sections represents a potentially significant resource for medicine and biotechnology. The antibiotic crisis, the growing resistance of bacterial pathogens to existing antibiotic drugs, is one of the more serious public health challenges currently facing human civilization. Novel microbial environments, where organisms have been evolving in isolation from surface ecosystems for long periods, are among the most productive sources for the discovery of new antimicrobial compounds. The deep cave microbiome of Krubera, largely unstudied, may contain organisms producing compounds with antibiotic properties that have not yet been identified or characterized. This possibility is speculative. Not every unstudied microbiome yields pharmaceutically significant compounds, but it is scientifically credible and worth pursuing. The cave's hydrology has practical significance for the communities of the Western Caucasus region. The karst aquifer of the Arabika Massif is a significant freshwater resource. The water that enters the cave system from the surface eventually emerges at coastal springs that have historically been important water sources. Understanding how this aquifer functions, how water moves through it, how long it takes, what processes it undergoes along the way, is directly relevant to the management and protection of this water resource. Changes in land use on the plateau above the cave, changes in precipitation patterns driven by climate change, and potential contamination events all affect the aquifer in ways that can only be fully understood if the aquifer's underground structure is known. Krubera Cave is part of that structure, and mapping and studying the cave contributes directly to the ability to manage and protect the water resource it represents. The biodiversity of the cave, the blind crustaceans, the deep springtails, the cave-adapted spiders and microbes, represents a living library of evolutionary adaptation. Each species in the cave's biological community has been shaped by millions of years of evolution in response to the specific conditions of permanent darkness, cold, food scarcity, and isolation. The genetic information encoded in these organisms, the biochemical solutions they have evolved for the problems of deep cave life, are irreplaceable. Once a species is lost, through extinction, through the destruction of its habitat, through changes in the cave environment that eliminate the conditions it depends on, that evolutionary information is gone permanently. The cave's biological community is therefore a conservation priority in exactly the same way that any irreplaceable ecosystem is a conservation priority, regardless of how remote or inaccessible it may be. But beyond all these practical considerations, Krubera Cave matters for a reason that is harder to articulate, but perhaps more fundamental. It matters because it is a reminder delivered in stone and water and absolute darkness that the Earth is larger than our knowledge of it. That the planet we inhabit contains spaces we have not visited, processes we have not fully understood, and records we have not yet read. This reminder is valuable in a cultural moment that sometimes seems to assume that the era of geographical discovery is over, that the Earth has been fully mapped, its secrets fully catalogued, its mysteries resolved. Krubera Cave is a direct refutation of that assumption. Here, within a mountain range that is fully mapped from the air and thoroughly understood in its broad geological outlines, within a country that has been continuously inhabited by human communities for thousands of years, there exists a physical space of significant extent that remains beyond the reach of human presence. The cave does not care about our maps. It does not conform to our expectations. It continues in its dark and patient way beyond the current limit of our ability to follow. Human curiosity, the impulse to ask what is beyond, to follow a passage to its conclusion, to measure what seems unmeasurable, is the quality that has driven exploration of Krubera from the first Soviet expedition in 1960 to the most recent diving push into its deepest sumps. That curiosity is not merely scientifically productive. It is, in a deeper sense, one of the most distinctively human things about us. We are the only species on this planet that asks where a passage leads when there is no practical survival reason to follow it. We are the only species that carries ropes and instruments into the darkness for the express purpose of understanding what the darkness contains. The abyss of Krubera Cave is, in this sense, a mirror. Looking into it, or imagining looking into it, from the warmth of wherever you are tonight, we see reflected back a version of ourselves that is perhaps older and more essential than our ordinary daily identity. The version that wants to know. That finds the darkness not only frightening, but also compelling. That cannot pass an unknown passage without wondering where it leads. Perhaps the greatest mystery of Krubera Cave is not how deep it is. The depth is a number, an extraordinary number, but still a number, still a measurement, still something that can be written down and compared and discussed. The greatest mystery is how much still remains beyond human reach, not just in this cave, but in the countless other karst systems around the world, whose surfaces have been walked across by human beings for thousands of years, without anyone guessing what lies beneath. Krubera is the deepest known cave, but it is not the only unexplored cave. It is not the only abyss waiting patiently within the Earth's body for a curiosity sufficient to follow it to its conclusion. Let us ascend now, slowly. There is no hurry. We began this journey at the surface, in the brief warmth of morning light touching the pale limestone of the Arabika Massif. We moved through the entrance, past the point where daylight gives up, and descended through 2 kilometers of stone and water and cold air and geological time. We have been down here long enough, in imagination at least, to have felt something of what the cave is, its scale, its patience, its indifference to the passage of human time. Now we begin the return. The ascent from the deep sections of Krubera Cave is measured in hours and days. The pitches that descended quickly must be climbed slowly, using rope ascenders, one careful movement at a time. The sumps that were dived on the way in must be dived again on the way out. The underground camps must be broken down, their equipment packed and carried, leaving the stone floor as close as possible to the condition in which it was found. This is not simply a logistical convention. It is a form of respect, an acknowledgement that the cave was here long before any human arrived and will continue long after all of us have gone. As you ascend through the cave's vertical sequence, things change in ways that are subtle at first and then increasingly pronounced. The temperature remains constant for a long time. The thermal stability of the deep cave extends through much of the cave's length. But eventually, in the upper sections, you begin to feel a very slight variation. The air is moving more noticeably. There is, perhaps, a faint freshness to it, the suggestion of surface air mixing downward through the entrance zone. the sounds change too. The sounds of the deep cave, the constant dripping, the distant rush of underground water, the deep silence that underlies everything begin to be joined by other sounds. The entrance zone has its own acoustic character, different from the deeper sections. The echoes are shorter. The space feels less enclosed, though the darkness may still be complete above you. And then, finally, there is light. Not much at first, just a suggestion of grey at the edge of your vision, so faint that you might mistake it for imagination. But it grows slowly as you move upward through the final passages toward the entrance. The grey becomes slightly warmer. The shapes around you, rock walls that have been known only by touch and lamplight for days, begin to resolve into visible forms. The texture of the limestone, which you have been reading with your hands, reveals itself to your eyes for the first time. The colors emerge, the pale cream of the calcium carbonate, the darker staining where minerals have run down the walls, the damp gleam of surfaces touched by flowing water. And then you are at the entrance. You step through the narrow opening into the outside air, and the contrast is extraordinary. The light, ordinary daylight, the kind you have lived in your entire life without giving it particular thought, seems almost overwhelming after the darkness of the cave. The sky above the Arabika Massif is enormous and impossibly open. The air moves against your face. You can feel the temperature changing with the breeze. There are sounds that have nothing to do with water or stone, wind, perhaps a bird somewhere, the distant sound of your own expedition, teammates already outside and moving about. The mountain around you looks the same as it did when you descended. The limestone is the same pale grey. The plateau stretches in the same directions. The same patches of grass and scrub occupy the same spaces they occupied before you went underground. But something is different, not in the mountain, but in the relationship between you and it. You have been inside it. You have been held within its body, moved through its passages, breathed its cool, still air, listened to its water. The mountain is no longer simply a landscape feature. It is a place you know from the inside, at least partially, at least as far as human knowledge currently extends. There is a particular quality to the light at this elevation in the early morning, a clarity and a coolness that feels appropriate for the kind of thinking that a journey like this invites. Standing at the cave entrance, with the darkness of the descent still vivid in memory, it is natural to find your thoughts moving through everything the cave contains. The geological time, hundreds of millions of years of ocean, uplift, fracture, and dissolution, compressed into the stone around you. The water, moving right now through passages you have just left, continuing its patient journey toward the coast in the same way it has been moving since long before any human being existed to notice it. The life in the darkness, the blind crustaceans, the deep springtails. The microbial communities on the cave walls, continuing their slow and ancient existence in the sections of the cave that are now above you as you stand at the entrance, and below you in the sections that descend from the bottom of your ascent. The cave does not know you have left. This is worth sitting with for a moment. The passages that you moved through with your lights and your ropes and your survey instruments have returned to their permanent condition, absolute darkness, absolute stillness. The slow drip and flow of water through stone the same environment that existed before the first expedition arrived, and that will exist after the last expedition is done. The cave existed for tens of millions of years before any human knew it was there. It will continue to exist in its essential geological character long after the specific depth record it holds becomes a historical footnote rather than a current fact. There is something deeply calming about this perspective if you allow yourself to settle into it. The world is very large. The earth beneath us is very deep. The processes that have shaped this planet, the movement of tectonic plates, the chemistry of water on limestone, the patient accumulation of marine sediments over geological time, operate on scales that dwarf anything in human experience. And yet here we are, small and warm and curious, standing at the entrance of an abyss that took millions of years to form, having descended a small fraction of its total length, having learned a fraction of what it contains, wanting to know more. That wanting to know more is not a frustration. It is, considered quietly in the morning light above the Arabika Massif, something closer to a gift. The world has not run out of questions. The earth has not exhausted its capacity to surprise and exceed us. There are still passages in the darkness that no human lamp has illuminated, still chambers that have existed in silence since before our species learned to speak, still rivers running through the stone in complete and patient independence of anything we do or think or know. The Caucasus Mountains are old in the way that mountains are old, not old compared to the limestone they contain or to the ocean that deposited that limestone, but old enough to have witnessed the entire span of recorded human history as a brief flicker on a geological timescale that extends in both directions far beyond our imagination. The plateau of the Arabika Massif has been weathered by storms we have no record of, crossed by peoples whose names are lost, and percolated through by water that fell as rain on a world that would be unrecognizable to us. All of that time has been patient. All of that water has been working. All of that stone has been slowly, quietly dissolving and reshaping and descending into new configurations of darkness. Tonight, wherever you are watching from, the cave continues. Right now, as you settle deeper into whatever comfortable place you have found for this evening, the water in the deep passages of Krubera Cave is moving in its cold, dark, unhurried way through the fractures of the Arabika Massif. The blind crustaceans in the deep sumps are moving through their lightless world, finding what nourishment the water brings them, living out the particular existence that millions of years of evolution have shaped them for. The speleothems in the upper passages are growing invisibly slowly. A fraction of a millimeter per year, adding one more thin layer of calcite to the record of this year's rainfall and temperature, extending a geological archive that began long before any human civilization existed to leave its own records. And somewhere below the deepest point that any human being has reached, beyond the sump where the cave divers' lights have finally failed to illuminate the continuing passage, there is more stone, more darkness, more water moving through fractures in the limestone toward an eventual emergence at the coast. More passages that have never felt the warmth of a human hand against their walls. More chambers that have been silent since the mountain first rose above the ancient sea and the water first found its way downward through the new fractures in the new stone. Whether those passages will ever be reached, whether the water flowing through them will ever be sampled and analyzed by a scientist curious about its chemistry, whether the potential biological communities in those deep sections will ever be found and described, these questions remain genuinely open. The technology is advancing. The curiosity is persistent. The expeditions will continue, each one pushing slightly further than the last, each one adding a few more measurement points to the survey, a few more meters to the known extent of the world's deepest cave. But the cave will always be larger than our knowledge of it. That is simply the nature of this place. It was built on a scale that exceeds what human exploration can fully encompass in a time frame that exceeds what human imagination can fully grasp. By processes that are still operating, still deepening, still carving new pathways through the limestone that future explorers, or perhaps no explorer ever, will one day follow. This is the quiet truth at the heart of Krubera Cave. Not a mystery in the sense of a puzzle waiting for its solution. Not a secret in the sense of something deliberately concealed. Simply a depth that exceeds the current reach of human curiosity and a stone patience that has no need of being understood in order to continue. The morning light on the Arabika Massif is gentle and clear. The limestone reflects it softly. The entrance to the cave is a narrow shadow against the pale rock, modest, unhurried, neither inviting nor forbidding, just a present, just open. Just dark beyond the threshold, as it has always been. Long after we return to the surface, the silent rivers beneath the Caucasus will continue their patient journey through the darkness, far beyond the reach of daylight, far beyond the reach of our lamps, far beyond the furthest point any human being has yet descended, flowing on through the stone in the quiet and the cold as they have always flowed, as they will always flow. Thank you for spending this evening in the depths of the earth with history's sleepy time. If this documentary has settled something quiet in you tonight, if the stone and the water and the darkness have given you something to carry gently into sleep, please consider leaving a like on the video and subscribe so that the next journey finds its way to you when you need it. And if you have not yet told us where in the world you are watching from, please do. It is one of the small and genuine pleasures of this channel to know how many different places are resting together in the same slow story. Sleep well. The cave will still be there in the morning.